Good morning from the Coachella Valley. We're going to give you a quick recap on what we learned about heat. Heat is the energy of moving molecules, and as a result, it's really hard to keep track of. The actual amount of energy inside of something with all of its molecules jiggling and wiggling and everything is actually called the internal energy, and it's abbreviated with the letter U. Um, But that internal energy isn't really important. What is important is when some of that internal energy flows into or out of the object. So if heat, that's the flowing part of the energy, if heat um, the flowing part of the thermal energy, if that heat flows into something, the internal energy of that thing will increase. And if heat flows out of something, the internal energy of that thing will decrease. And we use the letter Q for heat, and heat is measured in joules because it is a type of energy. The most important equation that you're going to use is that the heat that flows in and out of something is equal to the mass of that thing, which has to do with how much of it you have, the specific heat of that thing, which has to do with what the material is and how well it stores and or manages heat, and a change in temperature of the thing. That means that if the heat is going into something, that'll be a positive quantity, and if the heat is going out of something, that'll be a negative quantity. And you can see that from the change in temperature. If heat is flowing out of something, then the temperature is going to decrease, and the final temperature is going to be less than the initial temperature. That'll wind up with a negative number. If heat is flowing into something, the final temperature will be higher than the initial temperature, and that'll wind up with a positive quantity. And of course, this heat flow always stops when you reach thermal equilibrium, and I think I told my little story about that. So once you've done this, the most important thing that you can do with heat flow is to kind of just say that energy is conserved. So if you were to put two things in contact with each other, like let's say that you had a beaker and it was full of water, and that water was at 50 degrees Celsius. That's fairly warm. And then you had another beaker, and this one was full of water, the same amount of water, and it was at, say, 30 degrees Celsius. And they're both, let's say, 100 grams of water. That would be 0.1 kilograms of water. If you were to put these two things together, if you'd mix them into a larger container with all of the water in it, what would the temperature be? Well, when you mix something that's of high temperature with something that's of low temperature, heat flows out of the high temperature thing into the low temperature thing, raising its temperature. And this temperature drops, this temperature increases until they reach the same temperature, which I bet is going to be 40 degrees Celsius. And we'd have 200 grams of water, conservation of mass and conservation of energy. And the formal way to do this is to say that the heat that goes into one thing is equal to the heat that comes out of the other. Now we have to put a minus sign in this equation. We have to put a minus sign in because one of these things is naturally going to be positive and the other is naturally going to be negative. And if we don't put this minus sign in, you're going to have a mathematical impossibility where a positive number equals a negative number. You could indeed use absolute value bars and get rid of the negative sign. That will work for you, but this is actually a better and more formal way of doing it. Now, this is a pretty obvious example, and you may ask, well, why do we have to do this? Why don't we just say it's halfway between? Well, it is halfway between in this example because I've chosen water for both of these things, and I've chosen the same mass of water. But if the masses were different and if the materials were different, this would turn out differently. So we, in physics, a lot of times take an obvious situation to set up the formal thing that's going on, and then we can use the formal thing that's going on when our intuition breaks down. So for example, what if I had a cup of coffee? Now, coffee can sometimes come out of the coffee maker quite hot. Let's say it came out at 80 degrees Celsius. That's nearly boiling. That's way too hot. And let's say that I had, again, 100 grams of coffee, and I wanted to add a little bit of really cold milk to it. And the milk is essentially water. but let's add 25 grams of milk that was in the refrigerator. Now, refrigerator temperature, in Celsius, room temperature is about 20, and refrigerators aren't quite 0. They're not quite freezing. So let's call this 5 degrees Celsius. Well, now it's not quite clear what's going to happen. I mean, it's going to be less than 80 when we mix these two things together into my larger mug of coffee ready to consume. But it's going to be above 5 and less than 80, but we don't know exactly what it is. So let's figure out exactly what it is. Let's get this going here. So I'm going to go ahead and do this example over here. So we're going to say that the heat going into the cold thing, that's the cream, is going to be equal to the heat that's coming out of the hot thing, that's the coffee, and there's a minus sign in there. The heat that's going into the cold thing is the mass of the, let's call it milk. Mass of the milk, specific heat of milk, and change in temperature of the milk. Over here we have a minus sign, and we have the mass of the coffee, specific heat of coffee, and the change in temperature of the coffee. Okay, now I said to you before that coffee is essentially water and coffee is essentially water and milk is essentially water. So these two things are going to cancel out. Now, the mass of the milk is only 25 grams. I could put this in grams. I could put it in kilograms. I'm going to leave it in grams. The reason you can get away with this is that because it's grams on both sides, we're off by 1,000 on both sides, and it works out okay. If you're worried about it, put it into kilograms. Now, the change in temperature of the milk is the final temperature of the mixture minus the initial temperature of the milk, which is 5 degrees Celsius. Over here, we have the mass of the coffee, which was 100. And then we have the change in temperature of the coffee, which is the final temperature of the mixture. Remember, the final temperature of the mixture is the same. They're going to come to thermal equilibrium, minus the initial temperature of the coffee, which is 80. Okay, let's see what we can do here. 25 TF minus 5 times 25, which is 125, equals minus 100 TF plus, we have a minus here and a minus here, so it becomes a plus, 80 times 100, that's 8,000. All right, this is obvious. We need to get this negative TF term onto this side. We need to get this negative number onto that side. So we're going to bring 100 over here and add it to 25. We're going to have 125 TF. And we're going to get this minus 125 over there and add it to the 8,000. So that's going to be 8,125. And now it's pretty clear that the final temperature of the mixture is going to be 8,125 divided by 125, which is going to be, calculator, please. Okay, turning it on, clearing it out from what I did last time. 8,125 divided by 125 is 65. So my coffee, by adding this milk to it, will be down to 65, which is a lot closer to where I like to drink coffee. Okay, let me do something with you to show you how to solve these problems. When you're looking for the final temperature, and by the way, this process is often called calorimetry. Now, calorimetry is really the act of finding specific heat. But a lot of times, just mixing two things together and trying to figure out the final temperature falls into the category of calorimetry. But you use the same equations. If you're looking for the final temperature, this can become a little tedious because, as you saw in the previous example, the final temperature is in two places. So let's pre-do this one time the hard way. Let's start with Q in equals minus Q out, and I'm not going to specify what these two things are. So we have the mass of object 1, specific heat of object 1, change in temperature of object 1 is going to be minus mass of object 2, specific heat of object 2, change in temperature of object 2. Now, you don't have to take these notes. Just follow along and make sure I don't make any mistakes here, okay? So let's write out what these changes in temperature are. So this is going to be M1, C1, and then temperature final minus temperature 1, temperature 1 being the starting temperature of object 1. Over here we have M2, C2, and then TF minus T2. All right, distributing, yes, that's how to say it. Minus M2, C2, TF, my plus, because minus and minus again, M2, C2, T2. All right, we're going to pull the terms that have a TF together onto this side, and the terms that don't have TF will go onto that side. So on this side, we'll still have M1C1 TF, and then this one comes over plus M2C2 TF equals, now this goes to the other side as positive, M1C1 D1 plus M2C2 T2. Okay, now we can pull out the TF here. Factoring out the TF, we have TF times the quantity, M1C1 plus M2C2. And then over here, we have this thing again, M1C1 T1 plus M2C2 T2, or 2 D2. And now finally, to find the final temperature, you're going to take M1 times C1 times T1 and add to it M2 times C2 times T2, and we're going to divide by the quantity M1C1 plus M2C2. And let's put this in parentheses for fun. So this is a formula that you can use to find the final temperature whenever mixing. So let's call this the mixing formula. And the mixing formula, it simplifies whenever the specific heats are the same, like they were with our coffee and milk all being water, or if the masses are the same. And if you look at this, the only thing that's different, we have this M1C1 here and here, we have this M2C2 here and here, we just have T1 and T2. This is a weighted average. See, an average of T1 and T2 would just be T1 plus T2 divided by 2. But when you multiply T1 times this thing, and you multiply T2 times this thing, and then you divide by those two things added together, this is a weighted average. It's weighted by both the mass of the object and by the specific heat of the object. Okay, we'll talk about some ins and outs, but this is an important video about problem-solving techniques. Half of what we're going to do in Chapter 9 here is this kind of problem solving, either this finding the final temperature or just starting with Q in equals minus Q out. Let me put a box around this guy right here. Q in equals minus Q out. That's an important thing. All right, short video today. Thank you so much.